Hello everybody, this is Darmus. This is a remake of a video that I made 2 days ago. I'm remaking it now because I updated the paper that I wanted to talk about. So this new paper is about a very new prediction of my quantum gravity theory, SPD quantum gravity, space particle dualism quantum gravity. And it's very, very fundamental because it's a prediction that I could have made in 2005 when I started this theory. Because already back then I said that the wave function, the waviness of probability distributions is generated by elementary particles having this space particle dualism, being quantas of space that are complex surfaces that are oscillating. So the surface area is the complex number z, which you know from the amplitude of wave functions. And so we only see the real part of this complex space that we live in. And so when the real part goes to zero, then the particle becomes undetectable. And that's what's generating this waviness there. Now, you expect this to lead to interference pattern and this kind of things. But what is unexpected and what is different from regular quantum mechanics is that on one trajectory, on a straight path, let's say, the probability to detect the particle goes up and down like a wave, which is not the case in regular quantum mechanics, because in regular quantum mechanics you have the complex number z going around the origin of the complex plane, goes around and around, but the absolute value is always the same, and so the probability is always the same. But in SPD, quantum gravity, the probability does not depend on the square of the absolute value of the complex number, but on the square of the absolute value of the real component of the complex number, and that doubled. Now it has to be doubled because when you make a measurement, you cannot really find the particle out of universe. You cannot measure it outside the universe, so that's kind of an inaccessible state. And I also explain why it is inaccessible. Basically, when it's out of universe, where is it? Somewhere here. Yeah, here, normalizing probabilities. Basically, when it's oscillating in and out of the universe, basically it becomes an antiparticle, goes from particle to antiparticle, then to exotic antiparticle, then to exotic particle, and you cannot really have particles change. It would be a flavor oscillation, and you only have that with neutrinos. And the reason you have that with neutrinos is because the measurement time is longer than the oscillation period, and so that's why it's allowed to really oscillate into those other particle types. And I've also explored non-oscillating flavor mixing in chapter 3.10 of my book. There basically we look at contributions from other particle types to the mass of a particle, but without having the particle move from one particle into another particle. Like you don't see an electron morphing into a muon or a tau. You don't see that, but I show that there is still a contribution that contributes to the total mass of the electron, the muon, and the tau. Yeah, so let's go back a little bit. But when you have particles phasing in and out of the universe, basically, you can also better explain quantum tunneling, because sure, the position is uncertain, You don't know where in the room it is. In the particle, you measured it once, should still be in this room. But you should be able to know that it's in this room, it's not in the other room. But with quantum tunneling, it can just go to the other room. And that's a little bit counterintuitive. But when you know that it can phase out of the universe, basically, then it makes sense that it would be able to go into the other room, because it can't go through the wall when it's currently not in the universe. So yeah, so the interesting application or observation of this is wave imprints. So this is very different from interference pattern. Wave imprints is basically, imagine a photon hits the screen, and on a particular trajectory it hits the detector screen, and in that moment it's the real component is zero. It has phased out of the universe, so then the probability to detect it there is zero. And let's say that's the 90-degree angle from the emitter to the screen. Then you can ask the question, okay, by how much do you have to move the beam up in any direction? By how many degrees do you have to move it up so that it will again be zero there? Basically, that would be half a wavelength, because every half wavelength, the real component becomes zero. Goes to positive, then to zero, then to negative, then again to zero, then to positive again. So it's half a wavelength. So that's here you have half a wavelength. So this is the pathway length, and this is the distance to the screen. So you have some small angle here, and you see how the L becomes bigger than D through that angle. And then you set this length to be bigger by one half wavelength, basically, by half a wavelength. And then you can basically calculate what angle that is. If we take a wavelength of 650 nanometers, the angle is 0.026 degrees. And when the distance to the screen is about 3 meters, 3 something meters. This is from an example that I did in my room with a laser. And okay, a single picture cannot really capture this very well, basically also because of the resolution a little bit, and because it's so bright. But when you look at it with your own eyes, basically you see that there are a lot of little dark spots and bright spots, and they're pretty much close to the smallest scale where the human eye can still discern, which is 0.1 millimeters. But a lot of them, I think, are 1 millimeter. And what we expect are these distances here when you have concentric rings. But you would only have clear concentric rings if the photon source was totally point-like. Then you would have clear rings. But if it's many points, then you don't get clear rings, but you have you basically have a granular structure there. And on video it's much more clear than here, but as you can see, you see all these little bright spots and dark spots. And you may think, oh, okay, maybe this is due to the air in between, because it's not a vacuum. But that's not really plausible, because when you look at it, the bright spots and the dark spots are not moving. They're like stationary. They're not changing, or not in short periods of time. So those are very stable patterns. Yeah. And as I mentioned before here, normalizing the probabilities, you have to multiply by 2. Yeah, and then we can look at Roger Nelson's Global Consciousness Project. It is basically looking at random number generator output. and he works in parapsychology. But what people in that field usually do is they look at random number generators and assign meaning to the two possible outcomes, 1 and 0, if you call them 1 and 0. And for example, 1 could represent something good and 0 something bad, and then intention has an influence. But here in his project, he was just looking at non-randomness in general, not at particularly looking at more ones than zeros, but not by saying that 1 is better than 0, but simply looking at non-randomness, like having a long chain of ones or a long chain of zeros. And so I don't see this being directly linked to intention, but which normally is possible, but and normally occurs. But here in this project, he was basically looking at long chains of ones and long chains of zeros and linking them with big events that affect, have an impact on global consciousness, as he calls it. But here with this theory, you could say that it's caused by phase coherence, because every time you have phase coherence, you can have these effects here. And then you could have a not so random distribution. It's still random, it's still quantum random. It's not denying quantum randomness, but it's less random than you would think. And so longer than expected chains of ones or zeros would then be explainable without the observer effect. Of course, the observer effect is very important, but in this case, the random number generators are hidden and nobody's really looking at them. They're all dispersed all over the globe. And so if these not so random patterns have another source, then of course you would take them and link them to events in the outside world, but it's not necessary to do that according to this scheme here. And there's also the work of Simon Schnall, who's looked at non-Gaussian distribution in measurements of radioactive decay and other things, which he linked to cycles, geophysical cycles, year cycles in the solar system. But I don't know how strong that link is. I think what he observed is simply deviation from a Gaussian distribution, and that's very well explainable using SPD quantum gravity, because here you don't expect a totally Gaussian distribution. You expect there to be some additional patterns. And I think Simon Schnall might have he seems to simply have observed non-Gaussian structures, and that's what this paper here is explaining, basically. Okay, yeah, that is all for now. Thanks for listening. See you next time.